let's see. You'll see the PowerPoints. The review document is in bright space, and it looks like this. Get my finger out of the way. And then we have the key is also there. I just didn't make a copy. And the worked problems should look familiar. This is chapter 15, solutions. And we'll see how well I do today. I got a brand new clicker, and it makes a green light instead of a red light. I think that should be more visible, yeah, on some surfaces. Plus, I've got control of the mouse. That's what I was looking for, a new clicker that had mouse control. Let's see, there it is. There's a mouse moving around. I think if I'm gonna use the mouse as a pointer, I need to modify it so it'd be bigger, bolder, so it points better. But this is a new type of clicker that they call them gyro clickers. They have little gyroscopes inside, and they can tell your movement and translate it into cursor movement. It's pretty neat. And you can control the computer from here. Be that as it may, let's get on with the discussion. Okay, so we're going to look at chapter 15, solutions, today. And this is Thursday. Next week is spring break, so we won't meet next week. So that'll give you a little extra time to catch up or master this chapter. But you can, if you need to meet for any reason, send me a message. Email, take a little time to get to me. Text message on my cell phone will get to me quicker. And then we can set up a Zoom session. I won't be keeping regular Zoom hours, office hours next week. But I'm going to try to be in my office as much as possible anyway. So if you're in the neighborhood, stop on by. If you're not, connect with me some way, and we can set up a meeting face-to-face or Zoom, whichever the case, whichever suits you the best. Okay, so let's talk about solutions. If I get my clicker straight here. Turn that off for that. Let's see which way. There we go. Figure out which button goes which way. Okay. Early on, we defined a solution as a homogeneous mixture. And we typically think of solutions as solids dissolved in a liquid of some kind, like salt in water or sugar in water. And in this chapter, most of the solutions in fact, all the solutions we're going to deal with use water as the solvent. So you can dissolve gases in water, you can dissolve liquids in water, you can dissolve solids in water. But that's going to be our main focus for this discussions of solubility. Oh, we got another one coming on. Let's see who that is. Michaela. Okay. There you go. All right. So let's just get on with it. I mentioned what a solution was, and and I also used a term that I didn't define yet, the solvent. The solvent is is the larger component. So if you put a pinch of salt in water, it's obvious the solvent is water. And the salt would then be the solute. Now, you can have any number of solutes, but you can only have one solvent. And for 99% of the solutions, the solvent is the largest amount. And it's always the largest amount when you start making the solution. For instance, sugar water. If you have a certain amount of water, you start adding sugar to it, the sugar goes into solution. But sugar is extremely soluble. You can put a lot of sugar in a little bit of water. So eventually, the amount of sugar that's in your solution will exceed the amount of water. But since we started off with water as the major component, we hold to that all the way to the end. There are some exceptions like that where the solvent eventually becomes the minor component. But I had a professor tell me one time, I was trying to decide how to present some information in my dissertation. And he said, you call it operationally defined. In other words, you say whatever you want it to be. So what we're going to do is say that for 99.9% of the time, the larger amount is the solvent, and it's always the amount when you start. Okay, and then we can define the character of our solution based upon the solvent. So aqueous solutions are always solutions in which the solvent is water. And remember, we use when we define a solution in a reaction equation, right, we use AQ for aqueous. All right. So now that we've got those definitions down, these solutions, I mentioned earlier, solutions we generally think of in terms of a liquid, solvent, and a solid solute. But homogeneous mixtures can come in any form at all. You can have a gas in a gas, right? And that's what we have in our atmosphere. Our atmosphere is 78% nitrogen gas. So it would be the major component, and we would consider it the solvent. And all the other gases are lesser amounts, like oxygen then is 21%. And then argon is a little less than 1%. And then you have minor components past that. So that's a gas in a gas. The interesting thing about gas solutions is that when you put two or more gases together, they always make a solution every time, without exception. Because think about it. How far are the molecules apart in a solid, liquid, and a gas? Well, solids and liquids, the molecules are pretty close together. But in a gas, they're huge distances apart compared to the size of the molecule. So there's lots of room for everybody. That's why when you put two gases together, you always get a solution. We can mix liquids and liquids, like alcoholic beverages, right? Their water is the solvent, and ethanol is a solute, and then you have some other components depending on what type of liquor and what brand, whether it's a distilled liquor or whether it's a fermented version, whatever the case may be. Those are liquids. You can even have a solution of solids and solids. Brass is an example of that, where the solvent is copper. It's the major component. And solute is nickel. So you can't just put a chunk of nickel and a chunk of copper together and expect them to form a solution. It doesn't work that way, right? You know that those two solids are not going to mix. But if you heat them up, if you melt them and mix them together, and then let them cool again, now you have a solid solution. A case where you have a liquid as the solvent and a gas as the solute is carbonated beverages. Carbon dioxide dissolved in water with other things, of course, gives you carbonated beverages. And that's why when you open the lid, they pop. Because that gas doesn't want to have as much gas in the solution as we want it to be. So you keep it capped under pressure, and that keeps the carbon dioxide in solution. And then our traditionals, where you have a solid dissolved in a liquid. Okay, so those are solutions. There are quantitative ways of describing solutions. Up to now, we've described the qualitative. What's the major component? What are the minor components? But we need to know exactly how much of the solute is actually in a certain amount of the solution. And that's what we call solubility. So you can define it in terms of mass of the solute dissolved in a certain volume of solvent or a certain volume of the total solution, right? We're going to define those terms in a minute. But when we actually use the word solubility, we're implying that there is a limit, an upper limit to the amount of solute that can be placed in solution. And it varies. It depends on the nature of the solvent and the solute and how they compare with one another. Some solutions, like sugar water, are extremely soluble. You can put massive amounts of table sugar in water. And some are just slightly soluble. What's a good example? Silver chloride. Silver chloride is generally not soluble. But we know from experience that a very slight amount of that silver and chlorine will go into solution. Not much, just a little bit. Very slightly soluble. So there's a whole range of solubility. And we define that solubility in different terms. If you go to a reference manual, like the CRC handbook, CRC stands for Chemical Rubber Company. Their handbook has been in print now for decades, and they revise it every year. But it's got just pages and pages of physical and chemical data, and it's a good reference manual. But if you go in there and look at the solubility of a solute in a particular solvent, then it'll have it listed, and it'll say at this temperature, so many grams of solute will dissolve in 100 grams or 100 milliliters, depending on the solvent, of the solvent. So you can look up that data. All right. There's a difference between the way that an ionic compound goes into solution. And now we're going to focus on aqueous solutions, where water is the solvent. To narrow our focus. There's a difference between the way an ionic compound goes into solution and a molecular compound that is covalently bound, the way it goes into solution. When an ionic compound goes into solution, it breaks up into its individual positive and negative ions. Like in the example here is sodium chloride. So you get the solid sodium chloride is that cation-anion matrix, the crystal structure. But when you put it in water, it breaks apart into its individual sodium and chloride ions. Okay? So the point is, if you put 1 mole of sodium chloride in solution, how many moles of ions do you get? 2. You get 2 moles of ions. That's an important concept. And it depends on how many cations and anions are in the simple formula for that compound. Now, when you put something else in solution, like sugar, it does not break apart. Sugar, sucrose, is a molecular compound. It has covalent bonds between the atoms, and they are not broken when it goes into solution. So when you put 1 mole of sucrose in water, you get 1 mole of sucrose dissolved in water. That's it, as far as it goes. Okay. Generally speaking, when we talk about, I think we've talked about polarity, molecular polarity. I'm pretty sure we have. Let me refresh my memory here. Yeah, I think we did in some earlier chapter. The polarity of the molecule is not a complete charge on the molecule. It's a slight. And this is for, when I say molecular compounds, I mean covalently bound, like sucrose, versus ionic compounds. So the nature of the solvent and the solute, if they're similar relative to polarity, then they're more likely to form a solution. So example, if you have your water molecule here, right, there's your water molecule, and that's your solvent. We know that this water molecule is slightly positive here, and slightly negative there. So it has a polarity like that. It's a polar molecule. If you put an ionic compound in that solution and it goes into solution, some ionic compounds don't form good solutions. But if you put an ionic compound in, like sodium chloride, you get sodium cations and chloride anions. Right? And there's an electrostatic attraction between the and the positive. That's what holds them in solution. Right? So ionic or polar molecules tend to dissolve in polar solids, like water. Let's see. Instead of using sucrose, it's a complex molecule. Let's simplify it and use glucose, like sugar that circulates in your blood. It looks like this. Okay. Each one of these places right here, that's a carbon. Okay. And then we've got another carbon over here. H. And then we've got like that, and like this, and like this. Okay. These positions around that molecule where it has an oxygen and a hydrogen form hydrogen bonds. In other words, they're polar locations. This oxygen is slightly negative, that oxygen is slightly negative, and this hydrogen is slightly positive. So this is where the water molecule will form a bond because it's negative. And then the hydrogen on this side will form a bond with that negative. So for molecular compounds, if they have polar parts to them, they will form those intermolecular bonds, and that they will be in solution more easily. Okay. So here's an illustration of what happens to a sodium chloride crystal right here, right? Sodium ions, chloride ions. when we try to put it in solution, what happens? Well, these water molecules come in and form those bonds with the cations and the anions. But they're not individual molecules of water. Those water molecules, when they associate with the crystal right here, they're also associating with other water molecules on the outside. And there's a pull. Those other water molecules help pull. It's like a tug of war with a rope, and you have one team on one side and one team on the other. The more, if they're unbalanced, if you have more people on one side of the rope than the other side of the rope, they tend to win because they're helping each other. Well, these water molecules are helping that one water molecule pull that ion out of the crystal. And as it becomes dislodged from the crystal, more water molecules can come in and associate directly with the ion. And eventually it becomes what we call hydrated. It's completely surrounded with water molecules. And that's what we're showing right here and there. Okay. This is what I was mentioning earlier about the molecular compounds. They're not ionic, but they can have polarities for the complete molecule or for just portions of the molecule. In this case, we have ethanol, right? Alcohol, the drinking kind. It has one hydroxyl group, and it's slightly positive, and the oxygen is slightly negative, and that's where the water associates, right here. That negative oxygen associates with a positive hydrogen. And that intermolecular bond is what holds ethanol in solution. Okay. Oh, I do have a model of sucrose, table sugar. Sucrose actually is a combination of two different sugars. Like this one is the glucose that I drew you right here. And this one is fructose, right? Everybody's heard of high fructose corn sweetener. That's what they put in everything to make them sweet now. But when you combine both of those together with this, what we call a glycoside bond, you get sucrose. But you still got all of these OHs around here, and those are prime locations for water to associate. That's why you can put a lot of this stuff in solution, because there are plenty of places to attach water. Okay. Now, the other side, the flip side is where water is concerned, water is a polar solvent. If you try to dissolve a non-polar solute in water, it won't go because there's no interaction. There's no electrostatic attraction. For instance, where we have water and oil, right? When you're trying to make salad dressing, I don't know, some people don't do that anymore, but occasionally I make my own salad dressing at home. I just put vinegar in water in one of these little jars, like that Armour chipped beef comes in with a blue cap on it. Put that in there, then throw a little Mrs. Dash in there and just shake it up real hard. That has the effect of temporarily emulsifying and make very small particles of oil, but it's not a solution. It won't go into solution, this oil. So you have to put it on your salad really quick in order to, before it separates. Okay, there's no place for the polar water molecule to electrostatically attach to the oil. So we get this idea, this rule of thumb, like dissolves like. And what we mean is polar compounds dissolve, polar solvents dissolve polar solutes. And nonpolar solvents dissolve nonpolar solutes. So how is this solution on the molecular level? If we could get down small enough and see what's happening, what do we observe? Well, the process is conceptually presented in 3 steps. Now, we pull these 3 steps apart so we can understand it, right? Like I said before, nature just does what it does. And this is our way of trying to wrap our brains around what's happening when a solution forms. The 3 steps, number 1, let's see, how do I put this? Break apart the solute. Okay? Break the solute apart so that you have individual parts to it, either individual molecules or individual ions, whatever the case may be. And this requires an input of energy. The word for that is endothermic. So you got to break that solute apart. Second part is you break apart the solvent. Right? And that requires an input of energy. It's also endothermic. Right? So we've invested energy in this process already. Are we going to get any of it back? Well, in the third step, you associate. You associate solvent with solute. And notice I didn't say molecules with molecules here, because if it's ions, then we're associating ions with molecules. So I just said associate solvent with solute. That is, form those bonds between the solute and the solvent. And this is exothermic. This is an output of energy. Okay? So we put energy in here, we put energy in here, and we get some of it back here. So if you make a solution, for example, if you dissolve a solid in water and it gets warm, then it's giving off more energy than you put in. So that means this step, the exothermic step, is greater than both of these combined. 3 is greater than 1 plus 2. If it gets cold, then you put energy in, and you don't get a lot back. In that case, this is less than 1 plus 2. And hospitals use that all the time with their cold and hot packs, right? They're bags of water, and there's a little capsule inside with a solid. And you break it and mix that solid in with you make a solution inside the bag. And depending on which one you picked up, one might get cold, the other one might get hot. It's a different chemical inside the capsule. And it's all based upon this concept. Which one wins? Just is 3 bigger than 1 plus 2, or is 3 less than 1 plus 2? That'll determine whether it gets cold or whether it gets hot. Okay. Well, there's the rule of thumb. Like dissolves like. Okay. Looks like we're going to pause for answer a question. Which of the following solutes will generally not dissolve in the specified solvent? Choose the best answer. Okay, and we're also told to assume that they're all liquids. So which one will generally not dissolve in the solvent? So carbon tetrachloride mixed in water, ammonia mixed in water, methanol, that's wood alcohol. That's the kind, if you drink it, it'll make you go blind. And nitrogen mixed in methane. Okay, let's take the easy ones first. All right, we got any gases, dissolved in gases here? Yep, right here. Nitrogen mixed in methane, right? It says assume all the compounds are in the liquid state. Well, I think that needs to be corrected. This is actually a gas at room temperature, and that's a gas at room temperature. So this one is soluble. Okay. How about any polar molecules and polar solutes and polar solvents? Right? Notice here, methanol has that OH group on it. That's going to be a polar end to the molecule. And the solvent is water, it's polar also. So that one's soluble. Okay. How about this one? Oops, went too far, sorry. Carbon tetrachloride mixed in water. You need to know something about carbon tetrachloride. Carbon tetrachloride is going to be like this. With chlorine, 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 chlorine. Okay. And the bonds between chlorine and carbon are like that. What I drew was a tetrahedron. That's the geometric structure that governs its shape, but that's not the bonding. The bonding is actually, well, let me redraw it. Bonding is actually carbon here and chlorine here, and then there's a chlorine in the background here, chlorine, chlorine. This forms a perfect tetrahedron. So, do we have polar bonds? Well, yeah. All of them are polar. But guess what? They're all polar, pulling in opposite directions. I mean, they're balanced. So they cancel one another out. That makes this compound non-polar. So carbon tetrachloride is non-polar, and the solvent, water, is polar. So it's insoluble. Okay? Now the last one. Ammonia and water. All right? Ammonia is a gas at room temperature. They say treat it as a liquid. Ammonia looks like this. Oops, sorry. Ammonia has hydrogen there, hydrogen in the back, hydrogen out here, and a lone pair of electrons there. Right? So, is polar this way, this way, this way. Those bonds are polar. Plus you have this extra negative pair of electrons here. So the molecule is polar. So it would also be soluble in water. So the only one that's insoluble is A. Okay? All right. Wet my whistle. Okay, I mentioned earlier that there's a range of solubilities depending on the solute and the solvent and how they interact, their natures. So we're saying that the solubility of the solute in a solvent is limited. It's not infinite. In fact, if it were infinite, then you'd have all solute, no solvent. You wouldn't have a solution anymore anyway. So that's kind of a moot point. But we have descriptive terms for solubility. Before we get to the quantitative version, we have these descriptive, qualitative, or semi-quantitative terms. The first one, a saturated solution. When we say a solution is saturated, that means at that temperature, we can't put any more solute in that solvent. It's at its limit, right at its limit. Any more won't go into solution. It'll just do something. And if it's a solid, it'll just drop out. It'll just settle to the bottom. That's a saturated solution. So that's one way of thinking, is that's our reference point. Right? If we have less solute in the solvent than is maximally allowed, then it's unsaturated. That's pretty easy. It's either saturated or it's unsaturated. Now, there are occasions under certain circumstances where you can put more solute in the solvent and it'll go into solution than you would expect at that temperature. These are supersaturated. And the nature of a supersaturated solution is it's very unstable. So one way to do that is if you have a solid and you put it in, let's limit our discussion to water. If you have a solid that's soluble in water, right, you put in some, you keep putting it in until it is saturated. Then you heat it up. In most cases, you can put more solute in if the temperature rises. And for argument's sake, let's just assume that that's true in this case. Okay. So you put more solute in and it goes into solution at the higher temperature. Then you take your beaker off the heat source and you set it on a table and cover it and don't disturb it. Let it sit quietly and the temperature come back down to room temperature. And if you do it right, then all of that solute that you put in solution is still there in solution. It's now supersaturated. There's more solute in that solution than you would expect at that temperature. Now, what I mean by unstable, all I need to do to get that extra solute out of solution is maybe just take a crystal, a small crystal of the solute, the solid, and drop it in that solution. That forms that's a location called a nucleation site. And extra molecules that are in solution will attach to that one and it will just drop out of solution pretty quick, actually. Let's see, we had a video like that, didn't we? I think we did on a previous chapter where the scientist in the red coat had this solution and he poured the solution in there and it made a pillar. That's what was happening. The solution was supersaturated and he poured it on a bed of crystals and they started to come out of solution. And he just kept pouring it up and made a tall pillar out of that. That's what he was doing. Another way is to just reach inside the beaker with a sharp object like a spatula and scratch the inside of the beaker. It'll form little nucleation sites on the glass, and that'll cause it to come out of solution. Sometimes you can take your beaker and just shake it. So the point is, supersaturated solutions are very unstable. There we go. They're extremely unstable. All right. I repeat myself. Solutions are mixtures. They're homogeneous mixtures. And by being mixtures, the amount of solute can vary, right? And we can express that concentration in various ways in terms of the amount of solute that's actually in the solution. It can vary, and we can quantify it. We can say just how much there is. Oh, I've got some more qualitative descriptors. If we say there's the amount of solute is approaching the maximum, we say it's a concentrated solution. But if the amount of solute is very low with respect to the maximum, then we say it's dilute. All right. How do we express quantitatively these relationships between the solute and the solvent? And remember, if you only have one solute and one solvent, then there's only one value for expressing the concentration. But if you have two or more solutes, then each of those solutes can have a different concentration. Okay, the first way, mass percent. Well, I don't need to put it on the board, it's right there on the slide. Mass percent simply means what's the mass of the solute and what's the mass of the solution. Maybe I will put it on the board. So if you have, if you want to calculate mass percent, and sometimes we say percent M over M, which means mass of the solute, mass of the solution. So they have to be in the same units of measure. So it can either be pounds, pounds, grams, grams, kilograms, kilograms. They've got to be the same unit of measure. And we would say mass of the solute divided by the mass of the solution. Now remember, the solution, once it's made, has the mass of the solvent and the mass of the solute. So this term here is the mass of the solute plus the mass of the solvent. Right? This is equal to that times 100. That makes percent. Now, what's the usefulness of this one? It's really convenient. Right? You just measure the mass of your solute and measure the amount of solvent and add them together for the denominator. And then you put the mass of the solute on top. So the nice thing about this is it's impervious to temperature changes because mass does not change with temperature. Volume changes with temperature. Sometimes it's more convenient to use volume, and we'll do that in just a minute. But mass will not change with temperature. So this is, it's useful, very useful. Okay, so percent by mass, concentration of glucose in a solution made by dissolving 5.5 grams of glucose and 78.2 grams of water. So what's in the numerator? 5.5 grams. What's in the denominator? 5.5 grams plus 78.2 grams. Okay, there you have it. And your solution is 6.6 mass percent, or percent by mass of glucose. Now, another useful expression for concentration is called molarity. And it's the symbol for molarity is big M, capital M. We're safe using capital M because, for one thing, there are no elements in the periodic table with just capital M. There's some with capital M and some smaller levels like manganese and magnesium, but there are none with just M. So we can't get that confused with an element symbol. So this molarity is equal to the moles, and I abbreviate, I use my symbol for moles as little n. And it doesn't have a zero up here, so it's not a neutron, okay? That's moles, moles of solute, divided by volume, and that's volume in liters of solution. Okay? That's the definition of molarity. Now, the nice thing about this is chemical reactions occur mole to mole ratio. Remember, we've already established that. They don't occur mass to mass or volume to volume. In your written balanced equation, it's always numbers, moles, moles, moles. And the ratio is the coefficient of each of your parts to the equation, right? So if you're going to use, if you're going to do stoichiometry with a balanced equation, and you're not using mass as your entry point, but you're using concentration, putting two solutions together perhaps, then if you know the number of moles contained in that solution and how much of the solution, then you can step through stoichiometry much easier, rather than using mass percent, which would take a bit of a few extra steps of calculating. This is more convenient, right? Now we have this equation where we have M equals moles divided by volume. Remember, any equation, we can solve this for any one of those three. And if we have two unknowns, we can solve for the third one. So if we want to find the molarity, we just need to know the moles of the solute and the volume of the solution after we make the solution. Right? Remember, when we made our solution, we went through 3 steps. Right? We broke apart the solute, we broke apart the solvent. Sometimes we say we're making a whole, and then we put them back together. Well, when you put them back together in the solution, sometimes they don't use up all that space we created, or sometimes they get closer together, right? So the final volume won't be predictable. It has to be measured. So, but it's convenient to use this version, volume of solution, because what? Well, and once you've got the solution made, how are you going to measure out these parts? Well, it's not, the mass is not entered into this expression, so you have to use volume. You can't measure moles directly, but you can measure volume directly. So that's why volume of solution is more useful here. So now that we have this equation, we can solve it for, say, moles. Moles equals molarity times volume. So if you know the molarity of your solution, you know how much of the solution you have extracted from the reservoir, you can calculate how many moles of solute that represents. And then you go into your equation and just go moles, 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 moles. You're on your way. Okay, but of course, the one caveat that we have to be always aware of with molarity is this relationship to volume, because the concentration will change if the temperature changes. So you have to specify, and most of the time we say at standard temperature, which is 25 degrees. And as long as you stay close to 25 degrees, the concentration will not vary significantly. I mean, you could go down to 20 degrees or up to 30 degrees if you make it at 25 degrees, and you're probably safe within a very small percentage error. Okay, so that's another way to express concentration. Okay, here's an example. If we know we have, if we know we have 6 moles of hydrogen chloride in 2 liters of solution after it's made, we know we have 2 liters. Then we can calculate the concentration as 3 molar hydrochloric acid. How about this one? 1 mole of sugar in 125 milliliters of solution. What's the concentration? Well, remember the definition. Molarity is moles per liter. Right? You don't have liter here. You got milliliters. So you got to convert milliliters to liters. So how many liters is 125.0 milliliters? Remember? 1, 2, 3 to the left. 0.1250 liters. Now we can calculate. There's the conversion. In the denominator, that's where volume goes. And the moles go here. And then we calculate. 8 molar. This solution is 8 molar in sugar. I assume table sugar. Okay, what if you have this given to you? Potassium phosphate is soluble in water, right? That's the first condition. And then if you're told that, excuse me, went wrong way. If you're told that 500 grams of potassium phosphate is dissolved in water to make 1.5 liters of solution, what's the molarity? Well, do we have moles yet? No, we got mass, but we also have the name of the compound. That's why at the very beginning of this semester, I said, become proficient in naming and writing compounds, because they're going to come back and you need to know those. This is one of those cases. Potassium phosphate. There's potassium. There's phosphate. This has a 3- charge because it's a polyatomic ion. This one is an alkali metal, so it's a +1 charge. So now we know that we need 3 to balance the charges. So there's the formula, K3PO4. Now we can determine how many moles we have. How? Molar mass of the compound. So we calculate the molar mass of the compound. Let's see, here it is. Right? We have 3 potassiums, 1 phosphate, and 4 oxygens. And we get this value, grams per mole. And then we use that to convert 500 grams into how many moles of potassium phosphate do we have. Now that you know those moles, you can divide it by 1.5 liters and determine the concentration. We actually have 2.355 moles. And the molarity is 1.57 molar. So if we extract, if we pull out of a big vat of solution that's this concentration, we pull out 1 liter, then we know that there is exactly 2.355 moles of potassium phosphate in that solution. All right. Here's our calculation. What about this one? Now we're going the other direction. We have a solution that we know we're given 10 molar sugar. What volume of that solution do you need to give you 2 moles of sugar? It's like that equation, right? We know the equation is this. The question is, what's the volume that we need? So we solve for volume. Right. Put that one over here and this one over there. Now we plug in 10 molar in the denominator and 2 moles here, and that'll give us our volume. We need 2/10 of a liter, which is, for argument's sake, how many milliliters is that? 1, 2, 3. 200 milliliters of solution, because most of our measuring devices are in milliliters. So that way, you can say with 200 milliliters, we know that we have 2 moles of sucrose out of that concentration of solution. Okay. How about this one? So we have 2 separate solutions. Oops. Sodium hydroxide and potassium chloride. The sodium hydroxide is made with 100 grams, and the potassium chloride is made with 100 grams of those 2. Now, the first thing that should pop into your mind, are those equal moles? If we're going to calculate molarity, are they equal number of moles? And the answer should be instantly, no, they're not. You have to calculate exactly how many moles of each one that you have. So 100 grams of sodium hydroxide will be so many moles. 100 grams of potassium chloride will be so many different moles. But they're going into the same volume, 250 milliliters of solution. What's the concentration of each one in molarity? Right? So this is sodium hydroxide, right? 39.998 grams per mole is sodium hydroxide. And we find out from that how many moles we have in the numerator. And this is how many liters in the denominator. 250 milliliters is 0.250, extra 0. And then that calculation gives us 10 molar sodium hydroxide. Now, for your information, that is extremely concentrated. In other words, I would not want to submerge my hand in that solution. It would be very painful. First off, it would find any cuts that I have instantly. And then if I left it in there long enough, it would start eating my skin. How about potassium chloride? That's a little safer. Potassium chloride is a neutral salt. Sodium hydroxide is a strong base. So we do the same thing with potassium chloride, only now potassium chloride is almost double the molar mass. So we're actually going to have fewer moles of potassium chloride than we did of sodium hydroxide. But the volume is the same, right? Oh, I picked up another. Just noticed I picked up another student. Okay. All right, so we finished the calculation. Here we go. And the potassium chloride solution is 5.37 molar in potassium chloride versus 10 molar in sodium hydroxide. So the molar concentrations are different, even though the masses of the solute are exactly the same. Okay. Let's see, maybe we can make sense of this. We have 2 HCl solutions, and I'm going to assume that these are aqueous. So we have solution A, solution B, and they're aqueous HCl. So by that definition, they're both hydrochloric acid. Now, solution A, what's solution? A has a greater concentration than B. So the molar concentration of A is greater than the molar concentration of B. Okay, that's given. This is a word problem, and I'm extracting information from it. So which of the following statements are true? If you have equal volumes of both solutions, so now if we have equal volumes, so let's interpret this. This equals moles of A, well actually, it's moles of HCl per volume of solution. And this one is equal to moles of HCl in volume of solution. Okay. Now, that's easier for me to visualize it this way. If you have equal volumes of both solutions, solution B must contain more moles of HCl. Is that true? With equal volumes, if solution B has more moles of HCl, then it should be a higher concentration. This should be bigger, but it's not. This ratio is less for B. So A is false. How about the second one? If you have equal moles of HCl in both solutions, equal these, solution B must have a greater volume. If they're equal moles and you have a lower concentration, then by definition of quotient, the denominator must be bigger. So that is true. B is true. A is false. How about C? To obtain equal concentrations of both solutions, you must add a certain amount of water to solution B. What if we add more solvent to B? Does it get more concentrated or less concentrated? It gets less concentrated. So C is false. If you add more moles of HCl to both solutions, it will make them less concentrated. If you add more of these on both sides, it'll make both of them more concentrated than they were to begin with. So D is also false. The only one that's true is B. Okay? All right. Now we're going to go back to those solutions that are made from ionic solutes. Right? What do they do when they go into solution? They break apart into individual cations and anions. So if we have a 0.25 molar solution of calcium chloride, is there a question? Ah, okay. So this one breaks apart into calcium, one calcium, and two chlorides. So if we start off with 1 mole of calcium chloride, we have 3 moles of ions. Or we have 1 mole of calcium. If we're just talking about calcium concentration, it's equal, right? 1 to 1. But if we want to know chloride concentration, it's twice as much. So the calcium concentration will be 0.25. And the chloride concentration will be 0.5, twice as much. Okay? Now, if we're looking for total ionic concentration, it'll be the summation of those two, or 3 times this value, 0.75 molar in ions. Sometimes you need to know that. For instance, if you're in the medical profession, we don't have to do it anymore, but it used to be, we would mix up solutions for to to give to our patients intravenously. And once you mix them up and put them in the bottles, of course, you would cap the bottles off and put them in the autoclave and make sure that there are no germs living inside them. And then they'll store. And then you would use those bottles to deliver to the patient. Well, there's a concept called isotonic. And if you've had anatomy and physiology or a biology course, you probably know what that means. The strength, the concentration of solutes in the intravenous fluid must be the same concentration as the fluids in your body, or there will be dire consequences. If it's too low, your cells will explode. If it's too high, they'll shrivel up. But it could kill your patient. So it's important to know what the actual concentration is in solution. And this is not enough. You need to know the total ionic strength or ionic concentration in order to not kill your patient. Now, there's one other caveat to this scenario: solubility. If calcium chloride is not completely soluble, then you're limited by the solubility of the solute as to what concentration of ions you actually have in solution. But we can assume from this problem scenario that this is the total concentration in solution. So that calcium chloride is completely soluble at that level. So we can draw these conclusions without considering solubility. But it is a possibility in the future. If you're trying to determine the concentration of your ions, you need to know how much is actually in solution before you can say how many ions contribute. Okay. Which of the following solutions contains the greatest number of ions? There we go. For this type of problem, I use Henry Ford. Set up an assembly line. So if we set up an assembly line for this one, do on time. Let me see. Where am I? Let me check to be sure I'm not taking up too much time on these concepts. Yeah, I better move along. Instead of putting it on the board. So we need to know the number of ions in this solution because it says which one has the greatest number of ions. So we need to use our formula, molarity equals moles divided by volume, and solve for moles. So moles equals molarity times volume. So that's what we've got here. Molarity times volume is the moles of the compound. And then this 2 is the factor for how many ions per formula unit are produced in solution. And in the case of sodium chloride, there are 2, sodium and chlorine. So that's why the 2. We do that for each one. Right? Okay. So this one has 3 multiplier. This one has a 4 multiplier. And the last one is in there just as a reality check. Okay. Sucrose does not dissociate. So you can't answer the question for sucrose because it makes no ions. So we compare these 3, right? Total 0.08, 0.09, 0.08. So B, calcium chloride, under these conditions, makes the most number of ions. All right. So problem solving techniques. Got to ask yourself, what's the question? Right? What are they after? They're after ions. Total number of ions. So you say, what do I know? Well, I know the formula and I know the concentration. Right? Can I answer the question with that information? Turns out you can. Okay. So you can't just intuit the answer. You've got to calculate to get the answer here. You can't just look at the problem and touch your head and do, well, most of you are too young to remember Johnny Carson, but he used to do this character with a big turban on. He called the Great Karnak. And he'd have these cards with things written on them, and he'd touch them to his forehead and he'd know what was in the card. You can't just do that with these problems. You have to actually know how to calculate the number of ions to get the answer. Okay, what is a standard solution? It's just what it says. The solution represents a standard concentration. We know very accurately what the concentration of the solute is in that solution. Now, why would we need to know that? Usually, it's so that we can compare that solution with another solution. We may perform a chemical reaction with this solution and one that has an unknown concentration. And there's a chemical reaction that occurs between the two when you put them together. And the reaction, the product of that reaction gives us an indication for the concentration of the unknown solution. That's just one possibility. There are others, and you need to know accurately the concentration of solute in that solution. Well, how do you get there? Oh, I got a video.
Hi, I'm Jared Hyman, an assistant professor of chemistry at Elon University. Today, I'll be taking you through the appropriate technique and procedure for preparing a chemical solution. One of the most important abilities at all levels of chemistry is the preparing of a solution of a specific concentration. First, we'll define some of the terms used in this process. A solution is a homogeneous mixture of two or more chemicals. For the simplest solution, a smaller amount of one chemical, called the solute, is placed in a larger amount of a second chemical, known as the solvent. Today, we will be preparing a solution of sodium chloride, using a small amount of sodium chloride as our solute, added to a larger volume of water, our solvent. Before beginning any experiment, it's important to observe appropriate lab safety procedure and know the hazards of any chemicals you're working with. In any chemical reaction, it's important to keep track of the exact amount of reactants present, and for stoichiometric purposes, we use the term mole to define the amount of a substance. A mole is a counting term, similar to a dozen eggs, where 1 mole is equal to 6.022 times 10 to the 23rd things. As you can see, this is a really large number. The periodic table uses molar counting as a means of converting to a more experimental term of mass. For example, 1 mole of carbon atoms has a mass of 12.01 grams. In a compound such as sodium chloride, it's made up of 1 mole of sodium atoms with a mass of 22.98 grams per mole, along with 1 mole of chlorine atoms with a mass of 35.45 grams per mole, giving us a total of 58.43 grams per mole of sodium chloride. This means of using mass to determine the amount of a substance is useful for pure chemicals. But in the case of solutions, we now have a mixture of multiple different substances. Therefore, we express amount as a concentration. The most common unit for concentration in chemistry is molarity, abbreviated capital M, which indicates the number of moles of solute dissolved in a certain volume of the total solution. This gives molarity derived units of moles per liter. It is very important to note that this is a volume of solution, not the volume of solvent. Today, we will be preparing 500 milliliters of a 0.25 molar sodium chloride solution. Before beginning, it's important to map out your procedure for preparing this solution. Here, we'll look at the amount of sodium chloride we need in this solution. We know that we want to prepare a 0.25 molar solution, which means that there is 0.25 moles per liter of solution. We also know that we only want 500 milliliters of this solution, or a half liter. If we multiply these two terms together, we can see that we will need 0.125 moles of sodium chloride. From earlier, we can remember that there are 58.43 grams per mole of sodium chloride. We can determine that the exact mass that must be measured out is 7.304 grams of sodium chloride. In lab, obtain some sodium chloride in a clean lab scoop, and using a balance with some weighing paper, measure out as close to 7.304 grams as possible, marking down your exact mass. Note that if you go over the desired mass, it's never appropriate laboratory procedure to put the excess reagent back into the original container. Always use an additional container to collect the excess. Once you've measured out your solid and recorded the exact mass, transfer all of the solid to the appropriate sized volumetric flask. Volumetric flasks are made specifically for this purpose and should be used over other less accurate labware, such as beakers, Erlenmeyer flasks, or graduated cylinders. Here, we just transferred our solute to the 500 milliliter volumetric flask. If any solute remains on the weighing paper, use a spatula or a small amount of water to transfer the remaining salt. Next, add enough water so that the bulb area at the bottom of the flask is approximately half full. This will give you enough room to swirl the liquid, allowing the solute to completely dissolve. Again, it's critical that all of the solute is dissolved prior to filling to the appropriate volume, as different solutes may take up more volume in solution than their undissolved salts. Now that the sodium chloride is completely dissolved, we can fill the rest of the bulb area and some of the neck with water. You should now carefully and slowly add water, our solvent, as it begins to fill the neck. Once you approach the etched or printed line on the neck of the flask, you should add solvent dropwise, monitoring the location of the meniscus. Water, as a polar solvent, tends to cling to the glass walls of a flask. This phenomenon creates what is called a meniscus. The bottom of this curved meniscus should sit directly level with the line on the flask. At this point, there is exactly 500 milliliters of solution with an air of 0.2 milliliters. Different volume flasks have different air values. However, the air on a volumetric flask is much lower than any other type of glassware of similar volume. For example, the volume markings on a beaker or an Erlenmeyer flask are only accurate to plus or minus 5%, meaning if the meniscus were on the 500 milliliter line, it could be anywhere between 475 milliliters and 525 milliliters. On the other hand, using a volumetric flask, we know that the volume is exactly somewhere between 499.8 milliliters and 500.2 milliliters, meaning it's much more accurate. We now must determine the exact concentration of our solution by taking the mass that we measured out and dividing by formula mass for sodium chloride, 58.43 grams per mole, which gives us a total number of moles in our solution of 0.1253 moles. We can then take this number and divide by our volume of 0.5000 liters to give us a total exact concentration of this solution of 0.2501 molar sodium chloride. This value and the contents of the solution should be clearly labeled on the chosen storage container for laboratory safety protocol. You've now learned how to make a solution from a solid. Everything you need to do this demonstration in your lab is available from Carolina. We have experts who can assist you with any of your science demonstration needs. Visit us at carolinachemistry.com to see our complete line of products and kits for chemistry.
All right, that took a little extra time and he went through stuff that we've already covered. It's kind of simplistic, but repetition is not bad necessarily. He did make some points that I want to emphasize with this slide. So where are possible sources of error in making this solution? Every time you do anything in the laboratory or relative to a science, there is potential for error, right? Here's one of them. When you weigh out the sample, right? Your device may have narrow tolerances, and most analytical balances do have very narrow tolerances, but it's still not absolute. You can make errors there. You can make human errors in the way you measure things. How about transferring your solid into the flask, right? He mentioned knocking in little bits of your solid off of the paper into the flask. Yeah, well, maybe they're so small that you can't knock them loose, so you lose a little water. That's called a quantitative transfer, and it decreases the amount of error by using those techniques. Make sure all of the solute is dissolved before you finish bringing it up to the specified volume. It's got to be in solution and at room temperature. Right? Remember what I said earlier, when you dissolve something in the solvent, it can make it colder, it can make it warmer. If it changes the temperature of your solution, then the flask, which is normally calibrated at 20 degrees Celsius, won't be accurate. So if it gets very hot or very cold, that will bias your volume and introduce error into the preparation of your solution. All right. So I mentioned what could go wrong. Error measuring or transferring the solid, that could be impossible. Incomplete dissolution, that could be possible. You could, when you bring the solution up to that mark, let's see, let's blow it way up. So here's our mark right there. It's the top, and then there's the bottom of the flask. So when we bring our solution up to this volume, we want it to sit like this. The meniscus. So all of this is solution down here. And there's your meniscus sitting on the mark. Now, what if your eyeball should be here, perfectly level with that mark, okay? What if your eyeball is actually down here? Well, you're going to see them in two different planes. And you may think that your meniscus is on the mark, but it's not. Or if your eyeball is up here, which is more likely. So the error that's introduced by not being level is called parallax error. I think that's the way you spell parallax. So that's why you set your flask on the bench top, and then you move your eyeball to be level. Now, how do you know your eyeball is level with that mark? Well, that flask neck, right, has a mark all the way around. Both sides, all the way around. So if you're looking at it and you see a single mark, you're level. If your eye is below or above, you'll actually see two lines because you're looking at one line from the front side and another line from the back side from a different angle. That's how you know that your eyeball is level. Okay, that's one serious problem that develops for novice or unskilled lab workers. I mentioned this one, exo or endothermic reaction can change the temperature, and that will influence the volume. So what do? If you know that there's going to be a change in temperature, or if you can feel the flask and you feel it cold or hot, well, you bring the volume up, but not to the mark, several, maybe 2 or 3 centimeters below, and set it on the countertop and let it come to room temperature. And once it's at room temperature, or pretty close to it, then you do one final mix, and then you bring it to the mark. All right. Now, the concept here is dilution, right? We all have a concept of what dilution is. You take a concentrated solution and you add more solvent to it, and it makes it more dilute. In other words, you got the same amount of solute, but you increase the solvent, which is in the denominator of your calculation, and that changes the ratio to a smaller value. So you decrease the concentration by adding solvent. That's dilution. Why would we want to dilute a solution anyway? Well, it's a practical matter. I used to work in soils. Right? We would analyze soils for their fertility, and we would do that by extracting a certain amount of soil with a solution, usually some type of salt. And or an acid, as the case may be. But mixing up fresh solution every time you needed to do 100 or 200 samples in a day, it takes a while to prepare the solution. It's more efficient if you produce a small container of a very concentrated solution. And then when you get ready to use the solution, you dilute the concentrated to your working concentration. By dilution, you add more solvent. And we would do that routinely. Okay. So what we need to know is, what's the relationship? How do you do the dilution so that you know your working solution is the concentration that you expect? All right. Here's how it goes. This particular formula tells you what? Well, let me see. Do I have a slide coming up with that? Oh, I have another video. So let me let the video talk to you and see if it makes it. I'll correct any errors that are made in the video. But keep this in mind. This formula is what we're basing our dilution upon. And what we're saying is M1, V1, M2, V2. Remember, molarity equals moles divided by volume. So if we want to know moles, that's molarity times volume. So each one of these is relative to the number of moles, right? M times V equals moles. So in this context, we're saying that the concentrated solution times the volume of the concentrated solution that you extract from the container is equal to the molarity of the dilute solution times the volume of the diluted solution. And the reason they're equal is because that number of moles is exactly equal to that number of moles. Okay. We'll come back to that in a minute. But let's start the video.
Hi, I'm Jared Hyman, an assistant professor of chemistry at Elon University. Today I'll be taking you through the appropriate procedure and technique for diluting a solution. A common laboratory technique is preparing a more dilute solution from a concentrated stock solution. In this case, we are going to prepare a 0.250 liter solution of 0.01 molar. We know our stock solution has a concentration of 0.250 molar. The first thing we need to do is determine the exact number of moles in our dilute solution. We know our concentration needs to be 0.01 molar or 0.01 moles per liter. Since we know our number of moles per liter and we know the volume we need, we can calculate that we need exactly 0.0025 moles of sodium chloride. Knowing our stock solution contains 0.25 moles per liter, we can take the number of moles needed in our dilute solution and divide by the concentration of our stock solution to calculate the exact number of milliliters that must be transferred into our new solution. In this case, 0.01 liters of sodium chloride solution, or 10 milliliters. This is the stock solution of sodium chloride that we will be diluting. Make sure to pour the stock solution into another container before inserting the pipette into the solution. This is because you do not want to contaminate your stock solution. In this case, I'm using an Erlenmeyer flask. Notice that I have clearly labeled the flasks to adhere to proper laboratory safety protocol. To prepare our dilute solution, we will take a 10 milliliter aliquot of our stock solution using a 10 milliliter volumetric pipette. To use the pipette, place the pipette in the liquid to be collected. Squeeze the pipette bulb and allow the liquid to rise up the pipette. You should allow the liquid to pass the line marked on the pipette, but before the bulb. Remove the bulb and place your other thumb over the end, creating a seal, and slowly release just the corner of your thumb, allowing the liquid to exit so that the meniscus is directly on the line marked on the pipette. This takes some practice, and you may need to use the bulb to pull more liquid into the pipette again. Never pipette by mouth. Once you have the exact amount of liquid required in the pipette, hold your thumb firmly over the end and transfer the pipette to a new volumetric flask, in this case a clean 250 milliliter volumetric flask. Allow all of the liquid to flow out of the pipette. Do not use the bulb to force the liquid out, as pipettes are designed to deliver the exact amount of liquid, and there may be a small amount of liquid remaining at the end. Remove the pipette and follow the same procedure as before, filling the volumetric flask with solvent, again monitoring the meniscus until the exact volume is reached. You've now learned how to prepare a dilute solution from a stock solution. To see how to prepare a stock solution, you can view our solution preparation video at carolina.com/video. Everything you need to perform this technique in your lab is available from Carolina. Visit us at carolinachemistry.com to see our complete line of products and kits for chemistry.
There we go. So, he missed a few steps in there that good laboratory technique requires, but since there's no laboratory associated with this course, we'll not be too concerned with it. If you come back for general chemistry, then we'll go into the lab and I'll show you the things that he missed. But in general, the dilution procedure is correct the way it was presented. The key to this whole process is this relationship. Say, this is your concentrated solution over here, right? That's your concentrated solution. You're going to take out of this at a given concentration, you're going to take a volume out of that. Okay, what does that mean? That means now, in that pipette, for instance, you can calculate exactly how many moles of solute are contained in that pipette. And you're going to put it over here into your volumetric flask. It goes in here. Okay, how many moles did you put in that flask? Exactly the same number of moles that you pulled out of this one, right? So the number of moles now that are in the dilute solution are exactly the same. So you have the same number of moles over here as you did over here. Okay, so you know how many moles are being brought over here, and you also know the volume. So you can calculate the molarity of the dilute solution by the moles that you brought over divided by the volume of this device, of that volumetric flask. That's why dilution works. MCVC equals MDVD, or M1V1 equals M2V2. That's why it works. Okay. So I've got 20 minutes left and 20 slides to go, so I'm going to have to move along pretty quick. A 0.5 molar solution of sodium chloride in an open beaker sits on a lab bench. Which of the following would decrease the concentration of the salt in that solution? Okay. Decrease the concentration of the salt. Add water to the solution. Yeah. You add more solvent. You increase the value of the denominator. So the ratio decreases. So yeah, A is true. Pour some of the solution down the sink. No, that won't work. Why? Because molarity is an intensive property. It doesn't matter how much you have. The concentration is still the same. If I pour half of it down the sink, it's still that concentration. So B is false. Add more sodium chloride. Well, that's the wrong direction. You're adding solute. So that increases the concentration. So C is false. How about D? Let the solution sit out on the open air for a couple of days. What's going to happen? Well, let's see. You got sodium chloride and water. Sodium chloride is not volatile. Water is volatile. So the amount of solvent is going to decrease over time because it's evaporating. So there again, you're increasing the concentration of sodium chloride relative to the total volume. So D is also false. It actually increases the concentration of the solute. At least two of the above would decrease the concentration, not just one of them. Right? That one decreases. That's no change. And those two are increased. C, D, and D are increased, so E is false. The only one is A. That will actually decrease the concentration of salt in your solution. All right. What's the minimum volume of 2 molar sodium hydroxide solution needed to make 150 milliliters of a 0.8 molar sodium hydroxide solution? So we're taking a concentrated solution, 2 molar, and we're making a dilute solution. All right. So when you have a word problem like this, it's useful to set up a table for yourself. What's the molarity of the concentrated? How much volume of the concentrated? Molarity of the dilute, volume of the dilute. And put your values in here so that when you try to use the formula, you'll put your numbers in the right place. Right? If you put them in the wrong place, you get the wrong answer. So, concentration. What's the concentrated solution is 2 molar. All right. What's the minimum volume of that solution? This is our unknown. How much of that concentrated solution do you have to extract and dilute? That's unknown. What's the volume, the final volume? 150 milliliters. And the final concentration is 0.8 molar. Okay. Now you have your values. Okay, you're probably wondering, I hope, this is in milliliters. Should we convert that to liters? Well, you can if you want to. And then your answer will come out in liters. Right? If you got liters here, that'll be liters. Why? Because MC VC equals M D V D. If you solve it for Z, VC equals MD over VD divided by MC. Okay? So this is molar, this is molarity, this is molarity. Those units cancel. If this is liters, then that's got to be liters. But if this is milliliters, then that has to be milliliters. Why? Because the ratio is important. Now we're not an absolute formula. Molarity equals moles divided by volume. There, you must convert volume to liters. But in this case, where you have a ratio, it doesn't matter. You can leave it like that, and then your answer will come out in milliliters. That's why we left them as milliliters here in this formula. Then the answer is in milliliters, 60 milliliters. If we had converted to liters, what would that be? The answer then would be 0.060 liters. Okay. Now we're going to look at stoichiometry using solutions. We know stoichiometry using mass and moles. So at this point. Now with solutions, the only thing we need to do is, remember when we have an equation, a balanced equation, you can't go anywhere in that equation unless you have moles. So all you have to do is, if you're given a solution instead of mass, then the solution should have concentration and volume. M times V equals moles. And then you move on just like you would under any other circumstances. And these would be the steps. You've got to have a balanced equation. Sometimes it's useful to write the net ionic equation. That way you remove from the calculation those spectator ions. You don't have to, but sometimes it reduces the clutter. Then you need the moles of reactants or products, actually. Depends on which direction you're moving. Determine the limiting reactant. That's the same with solutions as it is with masses. Right? Once you know the mole, determine the limiting reactant, and we already know how to do that. Then calculate the moles of the reactant or the product depending on which direction you're moving. And then if you need to know mass, then you just convert those moles to mass. Or if you need to know the new concentration, then you consider how many moles of the product or reactant, whichever the case may be, and what's the final volume. Remember, the final volume is going to be a combination of the two solutions that you mix together. Okay, so here we have a problem. Let me see, do I want to do this one or do I want to skip to a later one? Okay, we still have acids and bases to talk about. 10 milliliters of 0.3 molar sodium phosphate solution react with 20 milliliters of lead 2 nitrate solution. And assume that the volume does not change in the process. Right? We have to make that assumption, otherwise we've got a very complex problem. So what do you need first? Well, you need sodium phosphate reacting with lead 2 nitrate. Sodium phosphate in solution reacts with lead 2 nitrate. In solution. And what's it going to do? Remember, this is a double replacement reaction. Right? Swap that one over here and this one over there. So we get lead 2 phosphate and sodium nitrate. Then you need to say, is there a precipitate formed? Right, so you look at that chart. Let's see, did I give you that chart yet? I think I did. In a previous semester. I mean, a previous chapter. Here we go. So there's your chart, your solubility chart. Right? And you can tell whether or not you have a precipitate, a solid. If you don't get a solid from this reaction, then there's no reaction. Right? You just got a solution full of ions. But if you form a solid like this one will, that's the drive for the reaction, forms that solid. Okay. So you have, I should have written this down a little further, but now we need to balance the equation. Right, so we have 3 leads on this side, we need 3 on that side. Now we have 6 nitrates, we need 6 nitrates. Now we have 6 sodiums, we need 6 sodiums, and that leaves 2 phosphates, 2 phosphates, we're balanced. You can go through the budgeting process and balance them yourself, but I'm pressed for time, so I did it quickly. Okay, 10 milliliters of 0.3 molar. So we have 10 milliliters of 0.3 molar solution. So how many moles do we have? Well, convert that to liters is 0.01 times this one would give you some value. Let's see if I've got it up here on the board. Yeah, first, what precipitate will form? We did that. Okay. Then we want to know what mass of precipitate will form. So we've got a stoichiometry here. Oh, I didn't write the rest of them. 20 milliliters of 0.2 molar solution here. So we can calculate the number of moles of that, the number of moles of that, and then we see which one's limiting. Right? Oh, we got several slides going on here. All right. What are the ions present? Balanced reaction. How many moles are present in the solution? Which one's limiting? Right? These procedures are just like stoichiometry we've used before. Okay. So what precipitate forms? Here we go. Aqueous, 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 solid. Okay, there's our precipitate. Come on, there we go. Then we find the limiting reactant. So this is how many moles of sodium phosphate we start with. This is how many moles of lead 2 nitrate we start with. Okay. Then we determine if we use all of the sodium phosphate, how much of the solid will form. Okay. 0.0015 moles of lead 2 nitrate phosphate will form from this reaction if all of the sodium phosphate is used. What if all of the wait a minute. We didn't do the other reaction. Oh, here we go. I got the animation out of order. Sorry. Here's the other calculation using lead 2 nitrate. So how much would it produce? It would produce less. Right? So that's your limiting reactant. Okay. Now that we know how much of this in moles can be produced, we can answer the question. What's the mass? We know that we can produce only this much of the lead 2 phosphate, and then we need the molar mass of the lead phosphate to calculate, we will get 1.08 grams of lead 2 phosphate out of this reaction. And you will have some of this left over. Let's see. This is the limiting. This is excess. So you're going to have some excess phosphate left over. And all of the original sodium is over here because it's a spectator. All the original nitrate, whatever it happens to be, will be over here. In solution still. But we will have some phosphate left over because this is in excess. So you can do a calculation of how much phosphate is left over in solution. That takes a little more doing, but it is possible. What's the concentration of nitrate ions? Okay, this was an easy one. Nitrate. How many nitrates did you start with? All right. Well, let's see. We had a concentration value for this compound, and we have 2 nitrates for every one. So it's twice the concentration of nitrates on the reactant side. So first thing we need to do is calculate how many nitrate ions are still in solution. All right, here's our balanced equation. Nitrate's a spectator. So we know that we have 0.04 moles of lead 2 nitrate. That means we have 0.008 moles of nitrate, right? Because we had 2 nitrates for every one. So that's how many moles of nitrate ions are present at the end because they're spectators. Now, what's the concentration? Well, we need to include 10 milliliters of original solution here, 20 milliliters. So it's 30 milliliters total. That's why we have to assume that the volume doesn't change in the process. But that's 0.03 liters. Okay. So there we have our calculation. This many moles of nitrate, so there's our concentration of nitrate, 0.27 molar nitrate in the reaction mixture at the end of the reaction. Okay, what's the concentration of phosphate ions left in solution after the reaction? In this case, we have to know how much phosphate was used up, how much we started with, how much we ended up with in the precipitate, and subtracted that number of moles from the beginning number of moles of phosphate. And then do the calculation for concentration like we did with the nitrates. So that's what we're going to do here, right here. We're going to use, in this case, we're using a net ionic equation. Since phosphate participates in the reaction, some of it's used up. We need to find out how much of it was used up and how much we started with. So we started with 0.003 moles of sodium phosphate. Right? So 1 phosphate per molecule means the same number of moles of phosphate as the number of moles of the compound. Right? So that's why these two numbers are equal. That's how many moles of phosphate we started with. Now, how much did we use? Okay. We used up in the reaction because here. This tells us that we have 0.004 moles of lead. How do we know that? Because we know how much lead phosphate was produced. We calculated that earlier. And the ratio of lead to phosphate is 2 to 3. In other words, for every 2 leads, for every 2 phosphates, we use 3 leads. So for every 2 phosphates, we need 3 leads. So we have this many leads, excuse me. Yeah, this is how much phosphate was used up in the reaction. So we subtract that from the beginning amount, and we find out that now we have 0.0003 moles of phosphate left over. Now we just need to calculate. That means we have 0.01 molar phosphate in solution left over after the reaction. There are some problems like that in the review document. So that'll give you some more practice. And we'll talk about those the first Tuesday we come back after spring break. Then we'll look at these problems. And if you have any trouble, in the meantime, contact me and we can conference somehow. Okay, now let's look at acid-base reactions. Because you can say what the concentration of an acid is or a base is, just like any other solution. And we can tell exactly how much, what is the concentration in molarity of our acid solution or our base solution. Now we know that if we add an acid to a base, they will neutralize. But unless they're exactly equal in molarity, then there'll be some left over from one or the other. When you put an acid and a base together, we call that a neutralization reaction. And the net ionic equation for an acid-base reaction, I think we'll be sure we've covered that. No, we haven't. Okay. The net ionic equation for an acid-base reaction is the hydrogen ions plus the hydroxyls yield water. That's the net ionic equation. For instance, it's already 11 o'clock, so I'm going to finish this discussion and it'll be recorded. Say we have an acid and a base. All right, what do? Well, the sodium and the chlorine combine, and they're still in solution. And then the hydroxyl and the hydrogen combine, and they make water. Okay, so this is a spectator, that's a spectator, those are spectators. So that's why we say that the net reaction is this for all acid-base reactions. If we have exactly the same number of moles of hydrogen ions as we do hydroxyls, then they will neutralize and we'll get nothing but water left. So the procedure for neutralizing sometimes comes in the form of, you know, the concentration of the acid or the base exactly. You prepared a standard solution. And then you want to add some of that standard solution to an unknown concentration of the acid or base, whichever the case may be. If you know the acid concentration, you add it to an unknown base, or if you know the base concentration, you add it to an unknown acid. And then once you've reached the point where exactly equal hydrogen ions and hydroxyls, you have titrated the solution to neutrality. And because you know exactly how much of one solution you've added times its concentration, you know how many moles of hydrogen ions or hydroxyls, and you can relate that to the total number that you were in the solution before. Then you can calculate the concentration of your unknown solution. That's an acid-base titration. So here we have a solution, actually a reaction, where we're adding sulfuric acid with sodium hydroxide. How many moles of sodium hydroxide are required to react with 1 liter of 0.5 molar sulfuric acid? Well, notice sulfuric acid produces 2 protons for each mole, for each molecule of H2SO4, whereas sodium hydroxide only has 1 hydroxyl. So it's going to take twice as much sodium hydroxide to neutralize a certain molar amount of sulfuric acid. And we just put that into an equation and balance it. I think that's what's coming next. Let's see. There we go. So here's the balanced equation. 1 sulfuric acid molecule plus 2 sodium hydroxide yields 2 waters and sodium sulfate. So now we can say how much, if we have 0.5 moles of H2SO4, which is 0.5 times 1. Remember, molarity times volume equals moles. So that's where this came from. This is the number of moles of H2SO4, and the ratio is the coefficients, just like any other balanced equation. 2 moles of sodium hydroxide per 1 mole of H2SO4 means you need 1 mole of sodium hydroxide. That answers the question. Now here's a unit of concentration for acids and bases. It's called the equivalent. 1 equivalent of any acid is the amount of that acid that gives you 1 mole of hydrogen ions. So for acids that have only 1 proton, if it's 1 molar solution, it's also equal to 1 normal solution. That's the term we use. Normality is equivalence of hydrogen ions per liter. And this side would be moles of HCl per liter. So when you have 1 proton per mole, molarity and normality are exactly equal. Similarly for bases, but it's in reference now to the hydroxyl ions. Why? Because the net ionic equation is hydrogen ions and hydroxyls equals water. Now here's another term that may throw you. Equivalent weight. That's the mass in grams of 1 equivalent of acid or base. Now, if this is 1.01 grams for hydrogen and 35.45 grams for chlorine, that's 36.46 grams per mole of that right there. So how much mass will give you a mole of hydrogen ions? This mass. How much mass of this will give you an equivalent of hydrogen ions? Exactly the same. So the equivalent weight of an acid that has only 1 proton is the same as the molar mass. But if we use something like this, say H2SO4, then its molar mass is 2.02 for the hydrogens, and sulfur is 3207. And then 4 oxygens is 64. 9, 0, 6, 7, 8, 9. 98.09 grams per mole. Okay. So the molar mass is 98.09 for sulfuric acid. But that gives you 2 moles of hydrogen ions. So how many grams would give you 1 mole? Half of that. So half of that would be 49. 49 grams would be the equivalent weight of sulfuric acid. Okay? And this is the author's idea of an explanation. I've already told you what it is, so we're going to skip that one. And notice here that for monoprotic acids, the molar mass and the equivalent mass are exactly the same. Here. HNO3, exactly the same. H2SO4, the equivalent weight or equivalent mass is half. If you had, and for sodium hydroxide, the two are equal. Potassium hydroxide, the two are equal. If we had calcium hydroxide, which has two hydroxyls, its equivalent mass would be half of its molar mass. Or if we had H3PO4, phosphoric acid, its equivalent mass would be 1/3 of its molar mass because it has 3 protons per molecule. Okay, here's normality. And it's defined as equivalents per liter. Equivalents of hydrogen ions if it's an acid, equivalents of hydroxyls if it's a base. We use a similar calculation to molarity. If you want to know the equivalence of acid, you need to know the normality and the concentration. And the volume, excuse me, normality and the volume in liters, and that will give you the equivalence. Right? So it's parallel to molarity in the calculations. Now, why would we want to go to all that trouble? Well, if you know the equivalents, you don't have to know where they came from. Right? When you put an acid and a base together, all you need to know is the equivalence of each. And then you can use the net ionic equation. And it doesn't matter where the hydrogen ions or the hydroxyls came from. Then the calculation is independent of the source. It's very useful if you do these type of calculations day in and day out. How about barium hydroxide? If it's used as a base, how many equivalents of barium hydroxide are there in 4 moles? Well, it should be 8 equivalents, right? Twice as many because you have 2 hydroxyls per molecule. Okay. And one last word. When you're doing calculations, remember we said MCVC equals MDVD. That works for molarity calculations. Okay? But if you're going to do acid-base calculations, you need normality. Then you don't have to translate from molarity to number of moles of hydrogen ions or hydroxyl ions. If we're going to do if we're going to do acid base, there we go. So now if you know normality, you don't have to know what the base is or what the acid is. Normality takes that into account. All right, that's it. I went over by 13 minutes. So have a good vacation and work sort of hard. Catch up if you need to. And I'll see you back here a week from next Tuesday.